The compatibility of units measurement system and design spacecraft structures for propulsion and navigation is not only critical but also one of the most important consideration for the security and the success of any space-related activity. Just for an example, the Mars Climate Orbiter began the planned orbital insertion maneuver on September 23, 1999 at 9:46 UTC. Mars Climate Orbiter went out of radio contact when the spacecraft passed behind Mars at 9:04:52 UTC, 49 seconds earlier than expected, and communication was never re-established. Due to complications arisen from human error, the spacecraft encountered Mars at a lower than anticipated altitude, and disintegrated due to atmospheric stresses. The primary cause of this discrepancy was that one piece of ground software produced results in a United States customary unit, contrary to its software interface specification SIS, while a second system, that used those results expected them to be in metric units, in accord with the SIS. The software that calculated the total impulse produced by thruster firings, calculated results in pound-seconds. The trajectory calculation used these results to correct the predicted position of the spacecraft for the effects of thruster firings. But this software expected its inputs to be in Newton seconds. Precision concepts for metrology that are performing incremental scaling mathematically can deform orders of magnitudes, and they do not necessarily have the same cosmological computation topology, meaning especially when they are used on a reference frame that is moving in conditions near the speed of light or above. An example of such deformation is the reverse square law, that is not absolute consistence measurement with the quantum field theory, especially for vacuum states descriptions. A renormalization concept for metrology is not necessarily the most appropriate way to handle statistically computations for precision. For example, the precision quest of renormalization operators in an effective field theory design. However, it is useful for educational practices to use the description values of a physical system in order to define it in a way. And for further documentation for structural material research, it is required to configure three determinations. 1. Determine the degrees of freedom, using an effective field theory. 2. Determine symmetries, definitions from their interactions, uneven indices, and levels of interactions that reveal boundless origins. 3. Determine the expansion parameters, leading order description like port accounting and the gauge theory, for example. Future spaceships engineers must always have the capacity to prove their design realities conditions which they are operate, with the most accurate manner. Every measurement technique must have the accuracy and the precision on what is measured. To this quest, logical systems for computations can vary in results, because they are in time variable dependence. Theoretically, time dependence frame produces a close relation between a measurement technique and the description for a physical system. These relations formulate the laws of physics, where we try to ensure the same repeatable analogy resulting in any given time. The compatibility of unit measurement is crucial. Performing incremental scaling mathematically can deform orders of magnitudes. Renormalization concept for metrology is not necessarily the most appropriate way to handle statistically computations for precision.